Hello everyone.
The title of my presentation is on the geometric red blue set cover problem. In this problem, we are given two sets of points. R is a set of red points and B is a set of blue points. We are also given a set of geometric objects, say O. The goal here is to find out a subset of given objects, say O prime, such that O prime covers all the blue points while covering the minimum number of red points. An instance of the problem is given here. One can notice that the cost of covering all these blue points is 2. So the red points are highlighted here. So in this paper, we consider several geometric objects ranging from intervals to rectangles to line segments. So in the case of intervals, we prove that the problem can be solved in polynomial time, whereas for the rectangles, the problem is NP hard. Even in the special cases when the rectangles anchored on two parallel lines, or even when all rectangles are stabbing a horizontal line. Further, the problem is also NP hard when the geometric objects are horizontal lines and vertical segments. We also prove that the problems are APX hard for several geometric objects. The objects are rectangles containing the origin of the plane, axis parallel strips, axis parallel segments, downwards shadows of segments, and rectangles intersecting exactly 0 or 4 times. First, we start with the case of intervals. Here we are given some blue points and red points, and also we are given set of intervals. The ith interval is denoted with a closed interval Li, Ri. We reduce the problem to the shortest path problem on a DAG. Say it is G. For every interval in the given instance, we consider a vertex in the graph G. And we also place directed edges between every two pair of vertices. And they will have some cost. We place the edge Vi, Vj only if Li is less than Lj and Ri is less than Rj. And all the blue points in interval Li, Lj are also covered by interval Li, Ri. Further, the weight Wij is defined as the number of red points covered by interval Lj, Rj that are not covered by Li, Ri. Further, we add a dummy source and a dummy sink to the G, and we connect these vertices with other vertices appropriately. One can note that the cost of shortest path problem from D1 to D2 is same as the cost of optimal solution to the red blue set cover with intervals. Since the shortest path problem on a DAG can be solved in polynomial time, the problem red blue set cover with interval can also be solved in polynomial time. Next, we prove a set of APX hardness results for the red blue set cover problem. To show that the red blue set cover problem is APX hard for several classes of objects, first we define a special red blue set cover problem with set system, and we prove that this problem is APX hard. Then we give encoding of this problem into the different set of classes of objects. Definition of special red blue set cover problem is as follows. Let R union B, S be a range space where R is a set of n plus 2m red elements and B is a set of 3m blue elements. And S is a collection of 6m subsets of R union B satisfying the two properties. One, for each 1 less than or equal to t less than or equal to m, there exist two integers I and j such that the 6 sets Ri bt1, bt1 rt1, rt1 bt2, bt2 rt2, rt2 bt3 and bt3 rj are in S. Further, each Ri belongs to exactly 3 sets in S, whereas other elements in exactly 2 sets in S. The goal here is to find out a subcollection S prime of S which covers all blue elements in B while covering the minimum number of red elements in R. We now prove that the special red blue set cover problem is APX hard by giving an L reduction from a known APX odd problem, which is the vertex cover on cubic graphs. So in the vertex cover on cubic graphs, we are given a graph G is equal to V comma E, where V is equal to V is a set of vertices, V1, V2, so on up to Vn, and E is a set of edges, E1, E2, so on up to En. The degree of each vertex in V is exactly 3. The goal here is to find out a minimum size subset of vertices V star of V that covers all edges in graph G. In the following, we construct an instance of special red blue set cover problem from a given cubic graph. First, for each vertex in V, we place a red element in set R. Further, for each edge, we consider 3 blue points and 2 red points, and we consider 6 sets as follows. Let T edges having endpoints Vi and Vj. The corresponding red elements Ri and Rj are already placed in the set R. Now we consider 3 blue points BT1, BT2, BT3 and 2 red points RT1 and RT2, and we consider 6 sets Ri BT1, BT1 RT1, RT1 BT2, BT2 RT2 and RT2 BT3 and BT3 RJ into the set S. Now we prove the bounds. Let V star is subset of V be an optimum vertex cover for G, and S star subset of S be an optimum solution for the above instance of special RBSC problem. Let Vi comma Vj be the Tth edge in E, where 1 less than or equal to I less than J less than or equal to N. Depending on the elements occurred in V star, there are 3 possible cases exist. First one, both Vi and Vj belongs to the vertex cover. Then in this case, we pick the sets Ri BT1 and BT3 Rj into the solution that into S star. So now, one more blue point is need to be covered. The cost of covering this blue point is exactly 1. Either you pick RT1 BT2 or the other side BT2 RT2. Now the second case, Vi belongs to V star but Vj is not belongs to V star. Then in this case, pick Ri comma BT1 into the solution S star, and now 2 blue points are need to be covered. The optimal cost of covering these 2 blue points is 1, like picking the 2 sets BT2 RT2 and RT2 BT3. Finally, the other case is Vi does not belongs to V star but Vj belongs to V star. This case is symmetric to the second case. So now in all the 3 cases, the cost of covering uncovered blue elements is exactly 1. Okay. So hence we note that the cost of S star is mod V star plus mod E. So since the graph is cubic graph, mod V star is greater than or equal to mod E by 3, which implies that the cost of S star, which is the total number of red points covered by the solution S star, is less than or equal to 4 times mod V star. Hence, we get alpha is equal to 4 in the definition of L reduction. Similarly, one can prove that beta is equal to 1 in the definition of L reduction. Hence, the special red blue set cover problem is APX hard. We now show that the geometric red blue set cover problem is APX hard for several classes of objects by giving an encoding from special RBSC problem. Let C1 is a class of rectangles containing the origin of the plane. The encoding is given in the figure A. First, we place all the red points R1, R2, so up to Rn on a diagonal line in the fourth quadrant. Further, we place all other points on a diagonal line inside the second quadrant, such that for any given t, the 5 points are bt1, rt1, bt2, rt2 and bt3 are always together in the same order. One can place rectangles for the sets in the instance of a special RBSE problem such that those rectangles cover the respective points. The encoding for the downward orders of segments is similar. In the case of axis parallel strips, first we place the red points R1, R2, so up to Rn on a diagonal line as shown in the figure. And we use the shaded regions to place other points. We also know that each red point Ri belongs to exactly 3 sets. Suppose if RiBT1 is the first set containing the point Ri, then the BT1 is positioned such that it is below the diagonal and to the left of Ri. If it is a second set, and BT1 will be placed to the right of Ri and below the diagonal. And if it is the third set, if the point will be placed on the above the diagonal and to the left of BT1. So the same principle works for placing the point BT3. Then other points will be accommodated appropriately and they will be covered with axis parallel strips. The case of rectangles intersecting exactly 0 or 4 times is similar to the axis parallel strips. Then the case of axis parallel line segments is also similar with a slight modifications. We now discuss our NP hardness results. The reductions are from planar monotone rectilinear 3-set problem. Each variable or a class take a segment. Variable segments are on horizontal line, positive class segments are above, and negative class segments are below. Class segments connects to the variable segments by 3 connections, namely left, right, and middle. First discuss the case where the rectangles are anchored on 2 parallel lines. The variable gadget is shown here. We consider 2 infinite lines L1 and L2. For each variable xi, the gadget consisting of 36m plus 4 rectangles. The 18m plus 2 rectangles are anchored on line L1 and the remaining 18m plus 2 rectangles are anchored on line L2. The rectangle T1i consisting of 2 blue points B1i and B36m plus 4i. The rectangle TJI contains 2 blue points BJ minus 1i and BJi. Further, the rectangle TJI contains the red point Rij. It is easy to observe that there are exactly 2 disjoint sets of rectangles T0i and T1i with alternate rectangles such that each set covers all the blue points and also covers the minimum number of red points, that is 18m plus 2. These 2 sets correspond to truth value of the variable xi. T1i corresponds xi is true and T0i corresponds xi is false. Schematic diagram of the class gadget is given here. Let CL be a negative class that contain variables xi, xj and xk in the order from left to right. Then we take 11 blue points and 8 red points and 4 rectangles anchored on line L1, and the placement of these points and rectangles is shown in the figure. For a positive class, the construction is similar by looking at the PMR 3-site instance upside down. We now prove that the instance of PMR 3-sat is satisfiable if and only if the instance of red blue set cover problem has a solution that covers at most 18mn plus 2n plus 6m red points. Hence, the red blue set cover problem is NP hard when all rectangles are anchored on 2 parallel lines. Next, we discuss the NP hardness result where the objects are horizontal lines and vertical segments. The variable gadget is shown in the figure. It consisting of 4 segments and 2 horizontal lines, and 6 blue points and 6 red points. The schematic diagram of interaction of variable and class gadgets is given here. The overall structure is shown here. The variable gadgets are placed horizontally, one after another from top to bottom. Each variable gadget has an area within which the gadget is placed. Inside each area, there is a portion called the variable region where the red and blue points of the variable gadgets are placed. The class gadgets are placed vertically one after other from left to right after variable regions. The gadget for the class CL consisting of 4 vertical segments, 5 blue points and 4 red points as shown in the figure. The vertical segments cover 2 blue points and 1 red point. For positive class and negative classes, the points are adjusted accordingly as shown in the figure. We prove that the instance of PMR3 set is satisfiable if and only if the red blue set cover instance has a solution that covers 3n plus 2m red points. Hence, the red blue set cover problem is NP hard. Thank you.